So in this video here, we're going to look into what happens or what do we do when we have a negative number under our root. But before we get into that, let's practice solving for x when we have x squared, where we have to use those square roots to help us cancel things out. So what we've learned from the previous lessons is that when you have x squared, and you're trying to solve for it, you're going to try to get the x squared by itself first. So in this case, I have a 3 in front of my x squared, so I'm going to try to divide it off so I can cancel out that multiplication. So I have to divide the other side as well. And the x squared now drops down 108 divided by 3. If you bring out a calculator, that gives you 36. Now, to get rid of a square, we've learned to take a square root, and that will help you cancel that part out. And I have to take the square root of the other side. Now, what we've learned is that when you take a square root, there's always a positive and a negative number. The square root of 36 is actually a nice square root. It's going to be 6, because 6 times 6 gives me 36. So this is a nice factor or root here. So we get our answer, x is going to equal positive 6 and x equals negative 6. And so that's expected when you have anything that's x to the second power, you're going to get two x values. Now with this one here, we have something in parentheses, but I want you to notice it's raised to the second power. So you cannot distribute this 4 inside if there's an exponent that's there. So I'm going to have to divide the 4 off so I can get the square by itself. So the 4 comes off. And now I have x plus 3 squared. 16 divided by 4 is going to give me 4. And then I'm going to take the square root of 2. And so the 2 and the root cancel, giving me x plus 3. That comes down. Whatever is inside the square in the parentheses comes down now. And then the square root of 4 decomposes into 2 and 2. So it is a perfect square root, but don't forget the plus and minus sign next to it. And so because this is a positive 2 and a negative 2, and I haven't moved over the 3, let's split this up into two equations so we can solve for the positive 2 and the negative 2. So I have x plus 3 equals positive 2 and x plus 3 equals negative 2. So that makes it a little bit easier to solve. So I'm just going to move the 3 over now. So subtracting the 3 over, that cancels. And I'm left with x plus, let's see, 2 minus 3 is going to give me negative 1. X equals, let's see, negative 2 minus 3 is negative 5. So it looks like my answer is going to be x equals negative 1 and x equals negative 5. And I also get two x values. So for this last one here, we have a negative 2 that's in front of our x squared. So we have to remove that to try to get our x squared by itself. So that will help me cancel. X squared now comes down, and 2 divided by negative 2 is negative 1. And you guys have heard me multiple times. If you have a square, to get rid of it, we got to take a square root on both sides. So the 2 and the root cancel. X comes down, and then I have this negative 1 inside of a square root. And when I think about decomposing it, let's just do it to the side here. So negative 1, if I were to decompose that, I would have 1 times negative 1, right? Negative 1 times 1 gives me a negative 1, and that's not a perfect pair. Whereas if I were to have something like square root of 1, well, 1 times 1 gives me 1. So that's a perfect pair right there. There are two identical numbers, so they can come out of the root. Pairs come out of the root, and that 1 can come out. Same thing with, when you take the square root of 9. 9's a perfect root. Then the 3 can come out. But it gets interesting. What if I had a negative 9? Well, that would be negative 3 times positive 3. And notice now they are not identical numbers. You cannot bring this 3 out of the root anymore. And same thing here. We have negative 1 and positive 1. You can't bring the 1 out of the root anymore because 1 is negative, 1 is positive. So we'll leave our answer like this for now. But I want us to take a look into today, how do we deal with a negative root? Because in the past, when we have a negative root, we just call it no solution. But I'm going to teach you today how to maneuver around it using some algebra skills that we're going to learn. All right, so let's get started with what we're about to learn, which is imaginary numbers. So imaginary numbers connect to the idea of what do we do when we have negative numbers under our root. So let me start off with a basic idea. Let's say that I, which stands for imaginary, this word imaginary, is being squared and it equals -1. So what I'm going to try to do is take the square root of both sides. So let's say you started with I squared and -1. You took the square root of both sides to cancel out the root. That means that I, or just when the variable is by itself, so no more squaring here, it would have to be the square root of -1. So today I want to focus on these two important things, which is when I, the imaginary number, is squared, you get -1, and when I is not squared, you have a negative root, or -1 under your root. So these two are basic fundamental things we need to understand about how we deal with negative roots. And let me explain why, and to put things together. So we call a root that has a negative number inside an imaginary number. And that has to do with history. So back in the day, humans were trying to create a vocabulary for numbers. And we start off with the basic idea of natural numbers. So natural numbers back in the day, very long back, like ancient times, natural numbers were numbers like 1, 2, 3, 4. Those whole numbers are what we think of natural numbers. And during those times, a lot of numbers were being questioned whether they could be accepted. Like 0 was not accepted for a long time. But we know that 0 is a real number, an important number that we use because we need to describe things where they have a neutral value, like 0, when you're trying to express a value of nothing. And then we also learned that negative numbers are really important numbers that happen to be in the real world. So integers came along. So like negative numbers do exist in the real world. At least to me, they feel pretty real because when my bank account goes negative, which doesn't happen a lot to Miss Chang because she's good with money, but if it were to go negative, that feels pretty real. We're in debt, right? And so when we're talking about real numbers in the world, we think of negative numbers, we think of zeros, we think of whole numbers. And then we start to add more numbers like fractions or what we call rational numbers. Put here rational numbers. Like, 1/2 is a fraction, 3/2, 4/9, whatever fraction you want to come up with. And then we get even more down to irrational numbers like pi, which end up truly existing in the world because we use it all the time to describe circles or things that are circular shaped. So these are kind of the building blocks of how we imagine what real numbers should be associated to. And then it came to a point where when we were solving algebraic problems, we encountered negative roots, and we just saw a moment ago that, when it comes to a negative root, we can't pull it out or do much with it because we get a negative and a positive number, and those aren't pairs. And so what we decided to call these, or what history decided to call them, is imaginary numbers. So what I want us to bring to the table to these problems is whenever we have a negative root, to use the symbol I to represent that, yes, it's an imaginary number, but I can still do the problem and work with the positive numbers at least. So these two statements here are actually pretty powerful. What it's saying is that if you have I, an imaginary number, it represents a root that has a -1 underneath. And in order to make it back to a real number, like these integers here, this -1, all you have to do is square the I and you get back to a -1, which is a real number. So I can kind of flip back and forth. And so let's kind of prove this idea here. So if I have a negative I squared, that's like saying I'm taking the I, which is representing -1, and I'm squaring it, right? And so what that means is I'm taking this number and I'm taking -1 and I'm multiplying it by -1. Well, when you do that, you can multiply the inside of the roots together. So -1 times -1 is a +1, but it's still under a root because both of them are under roots. All I did was multiply the insides together to get +1. And the square root of 1 is 1. And so I've just proved that if I declare that the imaginary number is the square root of -1, then I can figure out that I squared is just -1 because all I'm doing is taking this number and squaring it, and I'm getting back to a real number. So basically, the essential story to this is if I take an imaginary number and I multiply it by another imaginary number, I get back to a real number. But let's get into how do we apply it to these problems down here. So all of these are negative roots, and in the past, when you're in elementary or middle school, you would just say no solution. But I'm going to show you how the big kids or the algebraic kids and beyond algebra, how they deal with these problems. So when I'm given this problem here, first I want us to think of it as, okay, this 16 under this root is this 16 is being multiplied by a -1, right? If I can think of it that way, then I can imagine maybe breaking up these roots. So I can think of this as root 16 times root -1. Well, if this is a square root of 16, the square root of 16 is just 4, right? 4 times 4 gives me 16. So that's kind of nice. And then this right here, this piece right here is just I, right? Because I is just the square root of -1. So right next to the 4, I'll just drop down my I. So instead of having square root of -1 next to the 4, I can write this as I instead, which represents the square root of -1. But don't forget, because people often do, that you do need a plus and minus in front of the root because you're still taking a square root. There could still have been a positive and a -4 that came out. And so there is my answer. So now I'm dealing with plus and minus, and I'm dealing with i's. Let's try another one of these. So 49, if I were to think about it for a moment, the square root of 49 is 7. Plus and minus 7 to be exact, right? But there is a negative sign here. So technically, I would have had a -1 next to it if I were to decompose it. So technically, there is an I next to the 7. This is saying that, hey, I took the square root of 49, -49, and it's plus and minus 7, but it's an imaginary number because there was a negative sign under the root. And there we go. So what I typically do is if I notice there's a negative inside the root, then I know I should have an imaginary number or an I that's next to my number. And then I'll just take care of the root like I normally would with a positive number. And I always make sure I have a plus and minus sign if I'm taking a square root. All right, so notice how I can see that there is a negative inside this root. So I'm just going to go ahead and write this as root 52 and put the I on the outside because I know that this is going to give me an imaginary number because of the negative sign inside. Now I'm going to decompose 52 because 52 is not a perfect square root. If I were to think about numbers that divide into 52, I'm thinking like 13 times 4. 13 is a prime number, but 4 here can be decomposed into 2 and 2. And so I get a pair of 2's that can come out of the root. So I'm going to put the plus and minus 2 root whatever is left over, which is the 13. It's still a prime number, so I will put the 13 back inside the root, and the 2 comes outside because that's a pair. And I put the plus and minus because we are dealing with a square root, and the I needs to come down to the side. So some people put the I, after the root. Some people will put it in front of the root. It doesn't matter. But that there is my answer. All right, so let's get down into what is a complex number. So a complex number is a combination of a real number. So numbers like 1, 2, 3, fractions, pies, numbers that can be written on a coordinate system that we can see in the real world are real numbers. And then we have imaginary numbers. So when you combine real numbers and imaginary numbers, you get something called a complex number. So oftentimes you might see it as like maybe A represents a real number like 3, 4, whatever. And then a number that has an I next to it is an imaginary number. So when you combine them, you can call that a complex number. So you don't want to combine a real number with an imaginary number. Treat them like basically numbers that are not like terms. So we're going to work with these. I always like to think of i's kind of like a variable where you're combining like variables and then you'll just combine the numbers together, but you wouldn't combine a variable with a number. But there's something special about i's that we need to make sure it's in the playing field. I represents the square root of -1, and I squared represents -1. So keep these still in mind when you're solving, because sometimes you can change an imaginary number back to a real number if it is being squared. And I'll show you what I mean. But let's start with just adding and subtracting when it comes to simplifying expressions. So I can combine, in this case, the 3 and the 2 because they're both numbers. So if I combine 3 and 2, I get 5. The next thing I notice is I have 2 i's here. So that I have a 5i and a -4i. So if I combine those two, let's see, 5 minus 4 gives me 1 or 1i. So you can write this as 5 plus 1i, or you can also write this as 5 plus I. It doesn't really matter. Either of these are the correct answer. So sometimes people like to write the 1 in front of the I. Like I said, it doesn't matter. But you want to keep this the way it is because we don't want to replace I with the square root of -1. It just looks really messy. So we'll just write it as I. If we can say that I is just going to represent this number, we can use it. Now, for this part here, we can see there's a 3 and a 4. If I combine them, that's not too bad. 3 and 4 combine to give me 7. And I'll bring down the 6i since they don't have anything to combine with. So that is going to be my final answer. So what I'm doing right now just feels like combining like terms. Now with this one here, it gets a little bit tricky because I have a minus sign. And this is kind of like in parentheses. So I do need to distribute this negative sign in. Now this one doesn't have anything in front, so I can bring down 4 and minus 6i because there's nothing to distribute. But if I distribute the negative sign, I get -3 plus positive 7i. So if I were to combine like terms, I can combine the 4 and the -3 to give me 1. If I combine -6i plus 7i, that gives me also 1i. Or you can just say 1 plus I. So I've combined the numbers together to get the 1, and -7 plus 7, or -6 plus 7i gives me 1i. Now this one's going to be very similar, but I'm distributing a -4. And again, there's nothing in front of this guy, so I'm going to pull it down. So if I distribute the -4, I get -20 minus 24i. So if I combine the like terms, I have 7 minus 20. 7 minus 20 is -13. 2i minus 24. So 2 minus 24 is -22i. And I can't combine any further. So this is my final answer. All right, so we've done a little bit of addition, and like I said, you're just combining like terms here. But now let's try out multiplication and exponents, because that's where it gets a little bit tricky here. So with this first one, I have 8i, and I have it in front of a parenthesis, so I do need to distribute it. I don't have any exponents out here, so I can distribute inside. So I would get 16i minus 8 times 4 is 32. But notice this is an I and this is an I. If I multiply two i's together, I have to add the exponent, so this would be I squared. And so this is where the game changes. If I have something that is I squared, I can replace that. Let me bring down the 16i first and the 32. I can replace this I squared with a -1. So what I'm saying is I'm replacing this I squared with -1 because that's what the vocabulary says. If I have something that's I squared, an imaginary number that's squared, I would get -1. So I can replace the I squared with a -1, and I rather choose to so I can make it back into a real number. So I would now have 16i, two negatives, multiply, make a positive. So positive 32. And I can't combine these two, and so this is it. This is my final answer. And so what we're trying to do is basically, if we notice an I squared, we want to change it back to a -1. So that way we can combine more numbers if there are numbers to combine. So like this next one here, I have a 7i and a 3i that's in front of the parentheses. So I can go ahead and distribute that since there's no exponent out here interfering. So I have 7i that comes down. If I distribute a 3i times -8, that would give me -24i. Bring down the negative. 3 times 6 gives me 18. I times I gives me I squared. And so I can combine these two because they're both I to the first power. 7 minus 24 gives me negative, let's see, 17? I think -17. And then what I notice is that this 18 has a negative I squared next to it. So I can change that to a -1. So I've just replaced this I squared with a -1. So if I combine them and I multiply, I would have -17i plus 18. And I can't combine that any further, so this is all I can do. All right, for this next one here, it gets a little bit tricky, but all of these are basically in parentheses, so they're implying multiplication. And what I recommend is just the rule of thumb is that when you're multiplying, multiply left to right. It's just the way that we read. So if we multiplied the first two together, I would get -15i squared. That would be these two combined. Bring down the I that's next to it. Now, when I notice the I squared, that's where I definitely want to change that to a -1. So I basically have, in this case, that's a lot of parentheses. Let me write this way. So I have -15 times -1. So I bring down the 15, and I'm changing the I squared to a -1. And I'll still need to bring down the I that's next to it. So if I multiply -15 with -1, I get +15i. That comes down. So a lot of people, just the easy way to look at things is anytime they see an I squared next to it, they'll just go ahead and change the sign. So they might skip this step and just combine these two and make it a positive. Like same thing here. If I notice that this is an I squared, I'll just go ahead and change that -15 to a +15. So that's a little bit quicker if you can move that fast, or you're comfortable with moving that fast. Now, in the next problem, this is the one that trips a lot of students up, and I just want to show you the way that some students will do it, and it's not correct. So what a lot of students will do is they'll notice the 2, the exponent, and they'll distribute in and say that this is 8 squared plus 3i squared. And that's not quite right. And here's why. So anytime you have something that's squared, what it's being said is that it's taking the thing that you're squaring and multiplying it by itself, right? So this is saying if I'm squaring 8 plus 3i, then what I'm really doing is taking 8 plus 3i and multiplying it by another 8 plus 3i. And when you do this, you actually have to FOIL. And if you don't FOIL, you might miss out on some terms that you didn't see. So 8 times 8 gives me 64. 8 times positive 3i gives me 24i. If I multiply the other part, let's see, 3i times 8 gives me positive 24i. And 3i times 3i gives me positive 9i squared. So when I look at this, I can see these two terms combine, the middle terms combine. So I'm going to bring down 64. 24 plus 24 gives me 48i. Bring down the positive 9, that's to the side. But remember, this is a I squared, so it's really a -1 that's next to it. So what I really have is 64 plus 48i minus 9. So if I combine 64 with negative 9, I get 55 plus 48i just comes down. So I've combined 64 and negative 9 to give me 55, and the 48 comes down. And so I can't combine any further, so this is my final answer. And there we go. So that is it for this video. In the next video, we'll look at solving with square roots.